Hello, Takuya.
Hi.
Hi. You again.
Nice to meet you. Again.
I'm the chair today. I've been looking forward to this.
Okay, great.
It's always a pleasure. Um, so, since I'm the chair, of course, my job is to just make sure all the technicalities work.
Oh, okay.
So I will do this before I ask you how you're doing.
Yes.
Do you, do you want to just try and share the slides?
Try it. Okay. Yes.
And
Wait.
if you have video or sound, we can also test it out.
No particular video, so maybe it's okay. So there are several animations, but right.
Perfect.
Let's see. I'm opening the PowerPoint now. It's a little bit slow.
No worries. And I have also, by the way, because it said in our notes that we should not make the recording public
Mhm.
because some of the work is not published,
Yeah,
so we will
it's
not do this.
okay.
But
Uh,
two people have asked me if they could get the recording personally, and I thought I would ask you
yeah.
if you think this is fine or not. One is my student,
Mhm.
and the other is Simon Farmer, um, who I don't know personally. I'll just find out. He's at UCL. But essentially, I wanted to ask you if you would prefer that I don't share the recording with anyone, or if I just don't, or if I give it to
Uh,
these two people but not online. This is up to you.
so as for your student, it's fine. And could you send me later the name of the person, Simon Parr? And
What?
I will check the person and decide.
Okay,
Right.
maybe I can just give him your email, and he
Ah,
can write
yes,
you and ask you for the recording, and you can.
that's good. That's good.
Okay, I will do this.
Thank you.
Of course.
I don't know what happened, but the PowerPoint is not good. So I changed my PC,
Okay,
switch my
do this.
PC to the next one. Uh, wait a moment. This is not happening usually.
I mean, sometimes these things just happen suddenly.
Yeah, suddenly happened because the PC was rebooted.
Hmm.
And, yeah, recently some update of Office, Microsoft Office happened. I guess
Yes,
that's a reason. Um,
that's also why it's nice that we. Oh, sorry, I should admit you. That's why it's
yeah,
nice that we have just 5 minutes to test this beforehand, because
yeah.
95% of the time, no problem. But then suddenly sometimes happens. And, yeah.
Then now it should work. Let's see. Okay, so first I simply share the PowerPoint. So can you see my slide
Yes, I can see
in
it.
a small way,
Right.
not full screen? And now
Right.
I try to change to full screen. Can you see my full screen slide?
It's perfect.
Great. Thank
Okay.
you.
Okay.
Yeah, it's working. Thank you.
Exciting. I'm so I do not know any quantum mechanics myself yet.
It's no problem. So yeah, I try to explain first the basis of quantum computation.
Mm.
I'm also not an expert of quantum physics, but quantum computation is rather similar to neural networks.
Right.
So I would like to explain the parallel of neural computation, quantum computation. Maybe it's very much related to POMDP because
Mm.
POMDP represents the state as a vector, right? We have a vector of
Ah,
state. That vector is very similar to quantum state vector. So
that makes sense. Is the
yeah,
quantum state vector also a probability distribution?
yes, it's a square root of probability distribution.
I see.
Yeah,
That's very interesting.
yeah.
Yes, I suppose that in quantum mechanics, if I understand right, particles are
Mhm.
always distributions or probability distributions. And or is this right? Like or not particles. Quantum
Yeah,
mechanics is probabilistic or probability distribution based is my
yes,
intuition.
uh, it's a probability distribution,
Ah,
but it's a little bit tricky because there is a classical mixture.
mm,
Classical mixture provides a distribution,
mm,
but the quantum mechanics, quantum effects make different kind of distribution.
mm. I
That's
see.
a superposition of states.
I see. Yes.
Uh, the
Yeah. So
only
the standard probability uh, mathematics are different in quantum mechanics. Is this right?
yeah, a little bit
Yeah.
different.
Yeah.
So sometimes probability can be minus value or yeah, it's a little
Ah,
bit different. So we
okay.
don't think probability itself. We usually consider the amplitude of wave
Mm,
instead.
exciting.
Yeah.
And are you? It's. I mean, it's very exciting. It's also because it's a field I don't know so well, so it's interesting to learn about it.
Yeah, maybe it's,
Yeah. Yeah.
I hope it's interesting for everyone
At least for me, I think.
because,
Hi, Kyle.
you know, hi,
Are you in Japan now, Takuya?
yes, in
Yes,
Japan,
in Tokyo again.
Tokyo area. It's close to Tokyo. Yeah, it's my
Mm.
office, although it's
Mm.
foggy.
Mm.
It's still dark here in the United States. I'm I'm
All
I'm a
right.
I'm a physicist by training, so this should be like very interested in seeing this.
Oh, thank you for
Exciting.
joining. Well, it's midnight, right?
What happened?
Mm.
Is it midnight where you are, Kyle?
Oh no, it's like 6 a.m.
6 a.m. Okay. Still
Ah,
early.
six, not so bad. Not so good, but yeah,
Could
considerable.
be worse. Hey, Yosef. And Pia? I'm not sure I recognize your Zoom name, so forgive me if I don't know who you are. Or BIA. I will just
Mm.
send this email to Simon Takia, and then I think we can start soon as Carl is here.
Yes. Now I will share my screen. Okay. Um, don't- okay. Hmm. Right.
What is actually your background, Takia? I actually don't know. Think I know this.
Engineering.
Engineering. Okay.
So my childhood was yeah, like I was interested in making some AI kind
Mm,
of things, but not current AI. So I'm more interested in making something similar to a biological organism using mechanical things.
mm,
My
mm,
first motivation. And
mm,
to understand that, I think I need to understand what is the brain, how brain works.
mm,
So I start to consider the brain cells.
mm. That's
Yeah.
exciting. There are many paths into neuroscience. Yeah, I
Yes.
suppose. Yes. Hi, Carl. Welcome to the meeting.
Hi there, good morning.
Good
Good
morning.
morning.
So now that we're all here, I think we can begin the meeting. And I will just very briefly welcome very warmly Takuya Isomura here, who people who were at the International Workshop for Active Inference might remember for the zebrafish work, and who I'm sure also many people will recognize from the canonical neural network work, and that I at least find very exciting. But today he is presenting on quantum mechanics perspective on neural networks and active inference, and I've been looking forward to this for a while. So um, the stage is yours, Takuya.
Okay, thank you very much for your kind introduction, and thank you very much for Carl and organizers give me this opportunity to share a new idea with you. So today I'm talking about quantum extension of active inference, but before that, I would like to briefly mention about what I have been working on in these several years because it is related to my motivation to jump in the quantum things. So it comprises three parts, and the first motivation. Yo, yeah, I don't need to explain this here, but yeah, let me briefly explain. So Carl developed the free energy principle more than 20 years ago. And its statement is perception, learning, and action of all biological organisms are determined to minimize variation of free energy. And it is a mean to perform Bayesian inference. I often use this animation to explain free energy principle for people not so familiar to this field. But as you know, there is a animal which is our agent, and external world comprises some hidden information and observable information. The aim of our agent is to guess the external state through observable state, and having posterior belief is a promising way to do this. But to infer state correctly, those posterior beliefs are necessary to be updated. This is done by free energy minimization, and the free energy is characterized by generative model. So this model is also the subject of the optimization. This is done by making those parameters optimal in the sense that both state and parameter minimize a shared free energy. So by doing so, animal can infer the hidden state of external world and learn the external world structure. And this can be applied to optimization of action. Here we assume some prior preference, and by selecting the action that minimize the free energy in the future, our agent can maximize the probability to obtain the preferred input in the future. So this framework is referred to as active inference, and the entire scheme is nicely explaining what brain does when interacting with external world. So it is a theory for both perception and action. But as for neuroscientist, I'm a theoretical neuroscientist, so I would like to know more about the underlying mechanism by which neural network implement this sort of inference. So I worked out that. So our idea here is we start from evaluating neural activity equation, and this is a differential equation. And in many fields, including physics, the equation is often determined by the gradient of some energy function. So we take the integral of this equation and obtain energy function for a neural network, which we call Helmholtz energy. By contrast, in free energy principle or Bayesian inference, we first determine the model of external world, and then free energy. This is a variational free energy is automatically determined. Its minimization provides the solution of Bayes' theorem. So this is a Bayesian inference or variational Bayesian inference. And we show equivalence between those two cost function in the sense that there is a beautiful one-to-one mapping between the component of those energy functions. So recently I extend this framework to be incorporating the algorithmic computation aspect. Here, I extend the equivalence between canonical neural network and Bayesian inference to Turing machine in some form, in the sense that I first showed that this sort of canonical neural network have energy function, which is equivalent to energy function for Turing machine, some class of Turing machine. So yeah, simply speaking, this sort of neural network is Turing complete, actually, and not limited to Turing machine. This is equivalent to Bayesian inference. So my final conclusion is, assuming some dynamics that minimize energy. So neural network does this. And its solution, its fixed point, represent a mapping of Turing machine, as well as Bayes' theorem, solution of Bayes' theorem, which is a posterior belief. So simply speaking, this sort of neural network can emulate external algorithm by constructing algorithm within the neural dynamics. So it is a combination of Bayesian inference and the Turing complete computation. So I'm excited with this, but yeah, that's one extension of free energy principle. And I'm also interested in the experimental validation of this theory. My previous work focused on in vitro neural network and showed the consistency between empirical synaptic plasticity trajectory and theoretically predicted trajectory of synaptic weight. So their consistency indicates that free energy principle has the ability to predict the future learning process in this particular setup. And I'm now recently extending this framework to in vivo neural network of zebrafish, which performs some go, no-go task, decision-making task, and we record their data using calcium imaging and show the similar result as the in vitro study. So now we believe that free-energy principle has some degree of predictive validity that can quantitatively predict the learning process of individual animal. And in the future, I hope to extend this to mammal and finally human. So, as I said, the free-energy principle is indeed the principle. It's very centric to the neuroscience, and yeah, this can be applied to neurodynamics, Bayesian inference, and Turing characterization of Turing computation. And this can be validated by in vitro network and biological brain. And also some sort of machine learning are related to free-energy minimization. So it's good. So, but today I'd like to emphasize the limitation of this framework, which is the existence of many local minima. So what I've shown so far was a task or example in which local minima are very few or not exist. So we can converge their state into a global minima, which is a good solution state. But there are many bad solutions in which free energy is converged to some minima, but the minima is just assured solutions. So by converging to those solutions, animal cannot perform the task well, or prediction failed, or usually it doesn't work. So we need to consider the mean to escape from this sort of bad local minima. So that is the point. And this is also related to human level insight and creativity, to my opinion. So I'm recently interested in what is the computational theory of insight and creativity. So, so one possible model of creating new idea will be the creation of new generative model based on existing generative model. So each correspond to generative model, but in other words, this is representing some idea or algorithm. So by combining several idea or hypothesis, we can make a new hypothesis like this, and this may be related to the coming up new idea in the brain. And so by combining existing hypotheses, we can escape from local minima of free energy. So this can be this sort of insight can be a mean of non-local search, sorry. But there are still some limitations, which is computational complexity, because this is a classical modeling. So we need to evaluate each parameter set point by point. So although we usually consider a set of parameters that represent mean and covariance, but it is still information neighboring to a single point. So we don't see the entire solution space. So that is a limitation because of the existence of many local minima, we usually need to evaluate the goodness of each local minima point by point through this framework. So its computational cost can be exponential of number of state. That's a limitation. To address this issue, so I recently consider a possibility of quasi-quantum representation that leverage superpositional coding to enable efficient global search. So this is a kind of integration of quantum physics representation or mathematics into theoretical neuroscience. And the core idea here is conventional classical model represent the information as point, but quantum representation is based on the wave. So wave-like representation may be beneficial for accelerating the search. And there is some parallel between point representation and wave-like representation. So we usually represent hidden state posterior like this. So this is a S posterior expectation representing the probability of Si taking 1. And the bar or S bar indicates 1 minus S, which is corresponding to the probability of S taking 0. And very similar to this representation, we can define quantum state vector like this. So quantum state vector is a square root of probability if we consider a 1-qubit system. So even with the n-qubit system, the basic representation is same, as long as we consider the discrete state space in the external world. So this is a quantum representation. And if we extend this to n-dimensional system, n-qubit system, so this is a classical representation. If the hidden state comprises small n state, then we need to take account the n-dimensional vector. And this is formally correspond to the X here, which is outer product or Kronecker product of 1 bit X from X1 to Xn. So that is a very high dimensional state vector, comprises the capital N dimensional. So this occupy the entire space, entire state space, even though its parameter is same number as this model, because this cannot explain any possible combination of amplitude. So it only have the limited capacity of representing the waveform, but still it explains the form of wave in some sense. So unlike our intuition that to explain high dimensional information, we usually need a high dimensional parameter. So in this example showcases that even with a small number of parameter or small, so limited representational capacity, some high dimensional representation can be treated like this. So what we are seeing as point is on the other side have implication as a wave. So I would like to start consideration from this intuition and try to define the quantum neural network and quantum active inference. So that is the motivation. And if you have a question, please interpret and ask me anytime. So So I next move on to the explanation of quantum computing very briefly. So as you may know, this world is made of quantum. And for example, electron is an example of quantum. And our intuition of such a small particle is that each particle have fixed information of position and momentum, but it's not the case in real physical world. So real electron is like this. It's only expressed by the distribution or wave like this. And this sort of wave can be expressed by state vector or equivalently density matrix. So although this notation is not so popular in neuroscience field, it's same as vector. So if you like, you can rewrite this as a more familiar form like this. So it's just a vector. And density matrix. If the state is pure state, then density matrix is expressed by just a single state vector. So this is basically same things as considering product of two vectors like this. So it comprises square matrix, right? So density matrix is just like this. And the mixed state is more realistic in the sense that if some particle, quantum particle is interfered with other particle, or if we observe those particles, then interference make pure state into mixed state. So usually in the real world, everything are mostly mixed state in which the state vector is no longer explaining the entire information, but their classical mixture characterize those particles, set of particles. And if because this part represent a single eigenstate, if we consider the ultimate mixture of many states, it's their characteristic, which is expressed by the non-diagonal part of such a density matrix converge to 0. So imagine that. So this C, coefficient C, is determined to keep the trace of rho equals 0, because this is a condition to be a density matrix. So under this constraint, if we have many mixtures, then their off-diagonal elements converge to 0. So this reduced to a classical model, classical particle. So the pure state is most quantum-like state. It's is represented only by a single state. But mixed state are more classical-like. So so in the limit, we get the classical model again, by which no quantum effect occur. So that is quantum and mathematical expression of quantum state. And next, I move on to the quantum computing. Okay. Quantum computing. So recently, this field is very hot. So unlike several years ago, nowadays we can utilize a commercial quantum computer with hundreds of qubits. And each qubit corresponds to the classical bit, but they have different properties. So bit means binary information, so either 0 or 1. Okay, so if the state take either 0 or 1, it can have 1 bit information, right? And a single qubit, a single quantum state can have 1 qubit, which is expressed by the superposition of 2 states. So 0 vector here correspond to the 0 state, like this, and 1 vector correspond to 1 state, like this, the white state in this example. And we can add arbitrary weights to those superposition as long as they are square of x to be 1. And this can be extended to multi-qubit system. And surprising difference emerge when we consider high-dimensional quantum qubit system. Because, for example, if we have 3 bit, what we can express is only 1 of 8 state, like this. But 3 qubit can represent all possible 8 states simultaneously. So this information is much richer than classical information. So quantum computer basically use this parallel property to accelerate the computation. And it is often said that to explain the powerfulness of parallel computing or quantum computing. For example, if we have 300 qubit, that can express 2 power of 300 patterns simultaneously. This number is much larger than the atom or the atom in the entire universe, which is 10 power of 80. So at some level, classical computers cannot win this quantum computing. And the mechanism of quantum computing is as follows. So we have initial quantum state, x here. And again, this is just vector, as you know. And this vector can express the superposition of all possible patterns in parallel. And we often initialize those states as a uniform distribution. So each state have the same uniform amplitude, like this. So this is expressed by a wave. And through some interference, we can increase the weight or wave amplitude of particular state. In this example, if we want to increase the target state's amplitude like this, there are some transformation operators that can increase the amplitude of only of this target state. And this sort of operation is done by unitary operators. So unitary is a complex number extension of orthogonal matrix. So in real numbers, if this is dagger. So if u dagger times u is always identity matrix, then it is called orthogonal matrix. But now this is expressed by complex number, so it is called Hermitian matrix and or unitary matrix. And the update of quantum state is done by this sort of unitary transformation. So this keeps the property of required property of quantum state over the transformation because there is a Born theorem, Born's rule, which state that the quantum state vector, if we compute the product of square product of quantum vector like this, it should keep the number of 1 because this corresponds to the probability of this state. So the quantum wave amplitude is not equivalent to probability. Its square corresponds to the probability. So this value should be kept as 1 always. Anyway, through this sort of operations, we can change the state of quantum vector arbitrarily, as long as it can be expressed by unitary transformation. That is a tricky part. Some information, some operation cannot be expressed by unitary operators. So we need to carefully check whether the required whether the transformation can be expressed by physically expressed by quantum unitary operations. Okay, let's move on to the next slide. Yeah, this is a example of quantum algorithm, and which is this is one of the most popular quantum algorithm called Grover's amplitude amplification algorithm. That algorithm can speed up the black box search drastically compared to classical method. So this method required only square root n time computational cost to search an unordered database of n data. So as a comparison, for example, when we search all n unordered data point using classical method, it requires exhaustive search in order n time. So basically, if there's no hint and we have n choices, then we need to search all possible state or data to find a single answer, single correct state. It's trivial, right? But counterintuitively, if we utilize quantum computation, then such operation, such search can be achieved by only square root n order cost. That is surprising, and I explain why this happened. Quantum computer can represent a state U where all n points are superposed with equal amplitude of 1 over square root n. So this is a so-called uniform distribution, uniform state. And performing amplitude amplification operation these times, increase the probability of target state omega occurring being 1. So this is a target we hope to obtain, but it is unknown for the agent. And global algorithm can find this state very efficient manner. So it can be said that, let's say this is the best action. We have n capital N possible actions, and we need to select the best action to maximize the reward or to win the game. And if there is no hint, classical method need to search every possible state, but this sort of method can find the best solution, best action quickly. And global algorithm comprises two operations shown here. The first operation is a unitary transformation using omega vector like this. So it flips if the state is same as the target state. So now state are superposition of all possible state, but if the state corresponding to target state have some non-zero value, then this operation change the sign of corresponding state. And this is illustrated like this. Can you see that, this animation? So because now vertical axis correspond to the omega vector, and horizontal correspond to the vector which is orthogonal to the target vector. So if I apply the state, if I apply this operation to the initial state, which is a uniform distribution, we get this state. So this is the first step of global algorithm. And then we operate this unitary matrix, unitary transformation. So this is a operation characterized by uniform distribution. So I don't know how to explain this intuitively, but yeah, maybe for neuroscience people, explain this as a simple matrix is intuitive. So this is a matrix with substituting substituting identity matrix here. So we have a large minus value for diagonal, but because this is a very small positive vector or like this. So we have 1 over n value for all off-diagonal elements here and here. Okay, that is UU. And UU in this illustration correspond to reflection with respect to this vector. I mean, this direction, because this is exactly use vector's direction. So now we are here, and by applying this reflection, our position goes to here. That's interesting, right? So using two reflections, we can get rotation operation. So by applying single loop global operation, which comprises two different reflections, our state rotate to epsilon to the target state, where the epsilon is characterized by this. So sine epsilon correspond to 1 over square root n. So by iterating this method, so now by multiplying u omega again, we are moving to here, because the next reflection is with respect to this. And then again, we applied UU, which is a reflection with respect to this direction. Sorry, not this direction, with respect to the same direction here again. So we get here. So again, every step, the state approaches the target state with the angle of 2 epsilon, and finally reach the state of target like this. I got a question by chat, and first unitary.
I think Philip is commenting or just essentially restating what you were saying. Philip, would you like Takuya to respond to your comment, or is it mostly to be helpful?
No, it was just meant as a side comment. Just
yeah,
okay.
Thank you.
Okay. Yeah. Then I'll move on. Anyway, this move is very efficient compared to classical incrementation of the probability, because with only order square root n iterations, we can reach this target state through this sort of method. So if we combine this idea with sophisticated inference, in active inference, we may be able to accelerate the search of entire space of possible actions. So that is my idea. And okay, this is a quantum computing. And next, I briefly mention about quantum biology, because the largest question or doubt in this sort of talk is it possible that quantum effect can emerge in a biological system? So yeah, that is a very it's a natural, very natural question. And yeah, actually, several papers published in good journals such as PNS show that some biological effects are actually quantum. For example, one popular famous example of quantum effect in biology is photosynthesis. Photosynthesis effect is based on the energy transfer using quantum effect. The paper says not 100% photosynthesis are done by quantum effect, but quantum effect facilitate this sort of energy transfer. Another interesting example is magnetoreception. It's hard to pronounce in birds. So assuming that the birds move from one country to another country to escape from, I don't know, cold season. So yeah, there are some birds that move very far distance. Those birds can recognize the Earth's magnetic field. This is done by quantum device. Actually, the paper says that this sort of quantum device is placed in retina of birds, and they can detect the magnetic field of Earth which should be very small effect, but they can detect with very, very accurate sensors. So like this, biology and quantum are not so separated. Because we are living in quantum world, and why don't animals use the quantum effect? So yeah, it's natural, right? But those examples are realistic because those effects are happening within very short time and very small space. In contrast, if we want to make some meaningful quantum computing, we need to keep the quantum state, which is coherent state, long term without disturbance, and we need to make a large coherent state to compute something. That is the current status of the differences between so-called quantum computation and quantum effect. So quantum effect is much easier to realize. So quantum computing require a huge cost in both time domain and spatial domain. So we want to consider more plausible, or I want to relax the constraint to realize the quantum computing so that in ultimately I want to consider the crossover between quantum computing and brain computing as a long-term goal. But I think it's not so easy to prove that brain works as a quantum machine. So as a first step, I would like to integrate the mathematical tool in quantum physics to explain brain state, brain's neural network state, to explain, for example, efficient search or some inferences, or I don't know. But yeah, because it's just a mathematical tool, it must be in some aspect useful for characterizing event classical brain, right? So my first step would be like that. So incorporating quantum tool in brain science. And my ultimate goal, or my ultimate interest, is considering the possibility such that brain works in a quantum manner, in real quantum manner. But it's a long-term goal. So today I think I should focus more on the more short-term goal, which is explain brain using quantum tool. So that is second part. Do you have any questions or no? So lastly, sorry, I use a lot of time, so I briefly mention. I should rush and explain the last part.
It's very fascinating, Takuya, so no worries at all. But it's true, we should have time for your feedback, of course. So
yes. So I should speed up a bit. So the last part, and the first I characterize neural network using quantum state vector or density matrix. So considering that, assuming that hidden state is now expressed as the density matrix like this, and neural activity state are expressed by density matrix as well, and sensory input can also be a density matrix like this. So it's not necessarily a quantum state. So this can be a classical input. And our action is basically translated as a classical control signal and sent back to the external world. In this case, we can define information theoretic free energy like this. So I don't say this is exactly same as variational free energy in the meaning, but mathematical form is equivalent. So I explain this later. So by computing this free energy, we can characterize some level of information loss in this sort of system, neural system, and by minimizing, by deriving the dynamics of law here, which is a neural activity that follows the gradient descent on this sort of free energy, we can get a neural activity equation like this. And its fixed point corresponding to this closed form. This is corresponding to so-called quantum Bayes theorem, and which is also equivalent to quantum observable Markov decision process, QOMDP. I will explain this in the next slide. And one important thing here is that if we consider the classical limit of this model in which no off-diagonal value exists, then it is naturally reduced to a conventional classical canonical neural network. And here, in addition to this formalism, I assume this hypothesis, short-term intracellular global entanglement hypothesis. So this is a hypothesis such that STIGE neuron only transiently implement global entangled density matrix and quantum map operations based evolution within single cells. And global state are not globally entangled. This assumption enables biologically more tractable mean field quantum computation. So this is an idea to approximate conventional quantum computation in a more relaxed condition. So that is my assumption here. And this slide might be most important for people in this field. So this is a correspondence of the classical POMDP and the quantum POMDP defined here. So this system and the previous slide system are identical. So this is interpreted as a neural network, but this just interpret the same system as a POMDP or QOMDP. And free energy here is like this. So it is characterized by A matrix, B matrix, C matrix. But here, those operators are quantum class operators instead of conventional matrix. But they have very similar shape. So by minimizing this variational free energy with respect to S density matrix, we get quantum Bayes theorem. And if we consider the decoherence, complete decoherence, which is corresponding to diagonalizing this matrix, we get this relationship. So actually, the diagonal value of this matrix, density matrix, is same as posterior belief, posterior expectation in form of POMDP, classical POMDP. So through this correspondence, we can understand that if those matrices are decohered and those matrices A and B operators commute, then we can express the one-to-one correspondence of this quantum formalism and classical POMDP formalism like this. So actually, this new formalism is identical to classical formalism in this condition. So this emphasizes that this extension is natural, which is connected to the classical model in the limit. And this can be applied to perform some tasks. For example, in classical computation, blind source separation is one of basic tasks. So here we have hidden state, several hidden state. In this case, they are corresponding to speakers, and their speaker's voice are mixed, and our ears sense their signals. So our task here is decompose those mixed signals into the original sources. This can be done by minimizing mutual information or equivalent to minimizing free energy in some cases. And we finally get such a disentangled representation in the brain. So we can quantize this like this. So here, hidden state are expressed by product state of many state like this. So their outer product or Kronecker product produce the all hidden state. And sensory input are generated by through A matrix. Here, A matrix is corresponding to unitary operations, and our free energy is defined like this because we don't consider here the dynamics of external system. So we just try to infer the randomly changing hidden state from sensory input. And we assume that neurons, each neuron have disentangled state. So this product state corresponds to STIGE hypothesis. So each neuron is expressed only by its own density matrix. No entanglement exists between neurons. This can be computed by taking the trace out of the entire state like this. And the synaptic plasticity correspond to update of class operator or unitary operator in this case. And the unitary operator can be updated by minimizing free energy. Interestingly, its form is like this, which is similar to conventional Heppian and anti-Heppian plasticity form. And by iterating this dynamics, we can get the state that decompose the mixed sensory input into hidden state like this. And I also extend this to predictive coding. The story is very similar to the previous blind source separation. So I skip the detail, but now we incorporate the dynamics of external world, and it can be predicted by this sort of network. By the way, this network corresponding to QOMDP. So yeah, although I mentioned this as a predictive coding model, but in other sense, we can interpret this as a POMDP or QOMDP model. And finally, I confirm that this sort of method can predict the hidden state dynamics based on the observation, probabilistic observation. So yeah, I think that is the most interesting part, and also, but I don't have time, so I quickly mention that. So as I mentioned before, to perform sophisticated inference, if the possible choice, the sequence of n binary actions, then there are possible patterns to power of n. It is very large, so intractable in classical system. But if we consider the combination of sophisticated inference and the global algorithm, we may be able to reduce the cost to square root n. That's good, but conventional global algorithm has another cost, which is implementation cost. So to perform this, we need a lot of quantum gates simultaneously. It's very difficult to implement, especially in neural systems. So we would like to consider the mean field approximation of global algorithm. So this is a conventional one, as I explained previously. And this is a messy slide, but this is a possible implementation of mean field realization of global algorithm. So I separate the system into two levels. One is intracellular level and other is extracellular level. So intracellular level can have global coherence, but it is only transiently. So once it receives information and operate several global operators, and it release the information. It share the information with a single qubit system, which is another system, by using another unitary operation. We can little bit mix the state of this entangled global state and a single bit state. Then that is corresponding to the read out of information of this entangled state by a single qubit system. So by iterating this unitary evolution and read out, we can send the information of this intracellular system to the extracellular system. And to my best knowledge, this is corresponding to the conventional global algorithm with some cost. I explain what kind of cost can exist here. So this is two possible implementation. So I first tried the naive implementation of mean field approximation of global algorithm, and it showed that if we ignore the computational cost of intracellular operations, which is n power of 1/4, then its converging speed is almost equivalent to conventional global algorithm. So it's much faster than classical method, but still much slower than global algorithm itself. So its computational cost is evaluated like this. So n power of 3/4 times log n. So yeah, it's a little bit slower than as I expected. But I also consider the improved implementation of global algorithm, mean field algorithm like this. So with this implementation, I think and in the current stage that we can achieve the computational cost of square root n times log n, even with mean field implementation. So yeah, I'm still working on this part, but if this is a case, so I'm now working on a mathematical proof of this. But if it's a case, then we can say that even with more tractable implementation, mean field implementation, global algorithm can keep its efficiency. So I hope I can figure out this in near future. So anyway, its summary. So canonical neural network in classical case is equivalent to POMDP as we showed, and we now extend this to quantum regime in which neural activity and plasticity are expressed by density matrix and the Coulomb operators update, and it is corresponding to QOMDP, POMDP, quantum extension of POMDP. And this, I also propose STIGE hypothesis to make the quantum computing more tractable for noisy system like a neural network. And we show that those systems can perform brain source separation and predictive coding in a quantum manner. And also, importantly, quantum search algorithm like a global algorithm can allow the mean field approximation and keep some efficiency, which is better than classical search. That is the important point. So finally, today I'd like to discuss with you about such kind of things, because I'm very new. I myself is very new in this field, quantum field. So I want to write a first paper, submit that, and to do so, maybe the neuroscience emphasis of quantum effect is, it's risky. So I think it's better to emphasize more about engineering usefulness of this sort of work. And yeah, today especially I want to discuss with you about whether this sort of implementation is have mathematical validity as the quantum extension of free energy principle. And this is more like my task. So I want to clarify the computational complexity of the mean field global algorithm. So that is important to finalize the paper. And other things are more minor things. So last Friday, I discussed with Riken Quantum members, and they say that maybe 4-qubit system is too small, so I should extend the scale, for example, to 10 qubits. But another limitation of this sort of algorithm, I mean brain source separation or predictive coding method, is if I try to increase the scale, the probability to fail into should solution, local minima, increase. So I need to check the structure stability of those algorithms. And yeah, other further literature review will be important to show the feasibility of implementation for the quantum computer. That's it. Thank you. And sorry for a long talk.
Thank you for a very exciting talk, Takuya. Let's all unmute our microphones and give Takuya a round of applause. So before we start the discussion, I just want to, because I have written down in my notes that we should stop at 12 o'clock UK time, so an hour from now. But is that correct, Carl and Takuya? Do you have a backend today?
I have time, of course.
You have time, okay. How about
maybe.
you, Carl? Just
Yeah.
checking.
I have methods meeting in an hour and a half. Yeah.
In an hour and a half, okay.
Yeah.
So then that's good for me to know, because then I'll just make sure that there's time for your turn in the end as well. So if you have an hour and a half left, we can spend some time now on discussion from the group, and then you can take over, Carl, maybe when there's like in half an hour or something, I think.
Right. Yeah. Sorry, Peter. Yes, I've just known it's 11:10 in the UK. So it's an hour and 10 minutes.
10 minutes.
Yeah.
Perfect. Okay, I'll keep an eye. I'll keep the time in mind. So thank you, Takuya. Now there will be time for questions, for comments, and let's because you've been so nice to highlight the topics that are most important to you, so we can focus on them. But I'm sure there may also be other kinds of questions and comments from the group here. I certainly have many, but I'm not a quantum physicist, so I'll keep my I'll wait a little bit since I can't respond to the two ones you've highlighted here at least. Are there in the group anyone with questions or comments? And I'll keep my eye on that.
Comment from iPhone, someone's iPhone. Thank you for your feedback.
Yes, iPhone 57.
So a very interesting talk. I think you have a lot of interesting insights and ideas here regarding extending a quantum extension to the free energy principle. I hope so. I'm giving a talk later this afternoon in UK time regarding a physically plausible extension of these things. So I think there's points of interface and contact here that I would like to explore because a little bit more further, and I have to kind of get into my presentation and what I had to say about some of these things for this all to make kind of sense. But I think what you have here is honestly saves me a lot of work because and I think is it really from the engineering side of things interesting. And but I also, I mean, I've looked into quantum biology in prior research and things, and I know the examples you gave with like magnetoreception and avian migratory species in general seem to have the capacity to do this. Specifically, has to do with an effect called a Zeeman effect in a protein called cryptochrome in the eye. And also in the photosynthesis example, the example was light capturing is the main driver of the electron transfer, going from taking the photon and converting into kicking off the electron transport chain. So with all these things kind of in mind, whether or not there's a real meaningful quantum mechanical effects going on in the brain, that's an unsolved problem that's completely open. And honestly, I'm not willing to put my hat in the ring either way on that one because you have to prove it, right? So it just makes way more sense just to kind of take an agnostic approach to all that and to kind of see basically as a more sober view, if there is such a thing, this might be a tool or something useful to me to me investigate that kind of thing, especially regarding things that might be could be tied to or at least represented by some sort of quantum or kind of process, like you said, like you alluded to your example using creativity, I think, where you motivated this idea from, right? So I think also in terms of interfacing with the information theoretic construct that free energy principle is constructed from, I think that also is a nice tie-in because it connects with, because there's connections between information theory and physics itself, and also this quantum extended version of that. I think you've done a very good job here, and I think it was a very interesting talk, so thank you.
The comment, Kyle. You're the one presenting later today, you said, at the TNB?
Correct.
Yeah, okay. So I'm sorry for not having read up on that, because I'm not sharing that talk. So I'm ignorant there. But interesting or exciting that they're related to each other, the two. I see that Philip has his hand raised.
Hey, Takuya. Can you hear me?
Hi.
Yeah,
Yes.
thank you so much for that talk. Yeah. I was literally last week that I was thinking, can we use Grovers to optimize policy search? And so, yeah, I'm very happy to see that it does seem so. So I have a question regarding the mathematical validity. You said that you were, in some sense, uncertain about some points. You still want to make sure that it is correct. I was just wondering, I didn't have the time to, look into these formulas in detail, but what aspect of your formulation are you still uncertain about?
Oh, yes. So first, uh, first of all, I'm not fully sure whether this is a unique formalism or there are other possibility to formulate free energy minimization in the quantum sense. So maybe there are other formalism, but this is based on, to my knowledge, so recently people interested in the overlap of information theory and quantum computing, and some people say it's a cubism or something. It's a quantum-based field, and yeah, those people often use quantum extension of Kerr divergence, which is, to my knowledge, Ikegaki divergence or something. And yeah, this formalism is corresponding to those things. So this first part correspond to this is von Neumann entropy, and this is a cross entropy term. So their combination correspond to quantum Kerr divergence. So yeah, maybe it's good, but still I cannot rule out other possibilities. So that is one thing. And the more serious problem here is that mean field realization of global algorithm, because some operation is not allowed in real physical quantum computation. So I need to carefully consider whether what I thinking here it can be implemented in a real quantum system. So that is a reason.
Cool. Yeah. Thank you so much. I'd love to stay in touch and collaborate.
Yeah. Yes. Thank you.
Philip, you can reach out to me for Takuya's email unless you have it already. I had just a few brief questions, Takuya. They may be ignorant, so I apologize if they are ignorant. I'll try to keep them a bit short. Just one comment is that I know there is a field called quantum cognitive modeling, where people try to use quantum mechanics to make models of human decision making and so on.
Yes.
I'm not an expert in this field, but I thought you might find it interesting, at least insofar as motivating that in addition to being good for engineering, this may also be relevant for modeling decision making and cognition.
That's good question. So I said I'm joining Riken Quantum, right?
Say again?
I'm yeah. Maybe I didn't explain my affiliation currently. So I'm in Riken Brain Science Center, and my another affiliation is Riken Quantum. So which is a institute to investigate quantum computing, especially in the mathematical side. And can you see my browser?
We see it.
I'm here, so I'm a part of life science division of Riken Quantum. And those person, for example, Dr. Iliki is interested in quantum cognitive science and human evolution. He's working on humanity, or someone may know famous. Yeah, he's a famous guy, Dr. Ozawa. He proved the Ozawa's inequality, which is some extension of Heisenberg's inequality. And he is now working on quantum cognitive science. And yeah, I'm of course interacting with those guys. And yeah, as you said, they are very much interested in quantum cognitive science, but their idea is that brain doesn't necessarily isn't necessarily quantum. Quantum mathematical tool is useful to explain cognitive process. For example, if we take some ancate, so the famous example, I'm not sure if it's famous as well in UK, but for example, there is a vote of Clinton or Obama depending on the order of those candidate name, the result changes. That is related to incommute property of those operators. So they
Yes.
try to explain that using quantum tools. But
Yes.
we know POMDP. Why don't use POMDP to explain
Yeah, exactly.
that result? So yeah, to my knowledge, most such things can be expressed by conventional classical Bayesian framework, but they want to utilize quantum tools to explain that. So I am not fully commit those fields, but I'm very affected.
And
Influenced.
you clearly know it better than I do even. So that's
Yeah.
yeah. I think that their argument was that some paradoxes, for example, that
Mm.
people can prefer A to B and B to C, but also prefer C to A. Some of these
Yes, yes.
things that seem to not fit with expected utility, and I don't know how easily they can be described
Yes.
with classic Bayesian inference, like active inference. I'm sure it's
So,
possible in principle, but maybe. Okay.
I think their interest is, for example, if we use POMDP, conventional POMDP, we need to introduce the time
Mm,
change. But
mm,
with the quantum formalism, maybe we don't need the time,
mm.
explicit time, and can explain the same things.
Is this also true for the formalism you just showed now? That you wouldn't
No.
need to, right? Because it implements classic Bayesian inference, right? In a
Yes,
fast way.
yes.
Okay.
I always use time.
Yeah, good. And then the other thought was that so the tree search in sophisticated inference, which takes a long time, especially as you know, if you have many time steps and so on.
Yes.
It would be so. Firstly, it would be very exciting to get fast ways to do that. I was just talking to Tim Verblin from Versus, and they're trying to develop ways to do that and so on. But of course, tree searches are not unique to sophisticated inference.
Yes, yes.
And I just Googled a little bit, and I saw there is some literature on quantum tree searches and so on. Are you using the Grover algorithm, which I assume you also would know better than I do?
Okay. I guess your question is whether there another quantum or another any algorithm that fasten speed up the search.
But also that if you make this work, it's useful for quantum sophisticated inference, but also I think for any tree search, right? It's
Yes,
not
any
specific.
exactly any tree search. So that is based on the setup in which there are no hint. So this is a so-called black box setup, box problem. But usually we have some hint, which is expressed by the landscape of expected free energy. So we should exploit those information to facilitate the search speed. And the related things here is, for example, in quantum computing, there is a way to directly minimize energy and obtain the global global state, global ground state. That is called variational quantum eigensolver.
Okay.
That is very similar to idea of frequency principle. So by minimizing energy, it can get the best solution. And the way of minimizing energy is interesting. So in this method, we characterize posterior state vector by classical parameters, which is a parameter for quantum gates. So we can design quantum gate freely using classical parameters, and we observe the level of energy. So they call this as a Hamiltonian, but the idea here is very similar to free energy. So by computing the gradient of free energy or Hamiltonian, we can fine tune those parameters, and we get the best posterior state vector for our use. So that is a method. But one limitation is that there is no proof of quantum supremacy.
Okay.
So yeah, global algorithm clearly show the speed up compared to classical method by mathematics, but yeah, those heuristic methods have no proof yet. So
Yes. Thank you.
thank you.
And just to confirm, because I make software that runs active inference algorithms, and so I had this thought, I would like to implement this for the tree search here, but this would only be runnable on a quantum computer, right? Grover algorithm and so on.
If there is no hint, if this is a purely black box setup, then yes, it's only in the quantum computers. But if there are some hint, then it will be possible to fasten, speed up classical search to the square root order. That's a different story. Yeah.
Yeah. Okay. I'll stop asking any more questions now. Although maybe I will get chances later in the future also. Kyle, did you want to say something before we give the stage to Carl as well?
Oh no, I just wanted to reiterate, very interesting work. And I think I'm curious to see how this goes, because I'm also be interested in collaborating, especially yeah, in future work, because yeah, I think there's a natural overlap between what you're doing and some of the stuff that I've been trying to work on. So I hope you stay for my talk, or be able to, because I would like to have a better conversation with you. And I think after my presentation, we'll be able to have a better conversation, I think.
Yeah. So when your talk start?
Was it like be 9? Is it 9:30 my time? Which is like, it's a 2:30 UK time, I think.
2:30 UK.
That's 3 hours from now.
3 hours from now.
I try to connect.
It would be awesome if you could. If not, it's no big deal. But we'll find a way to connect, and I'm sure. But yeah, I see natural overlap here, and it would be really good.
I'm very interested in your work. So one thing I want to ask is that same link? I mean, I don't usually join the meeting, so same
it's
link.
The same
okay,
link.
okay,
Yes.
okay. I will join.
And I'm happy to forward the recording and so on. So get in touch with me if you need anything in this context.
Yes.
I'll put you in touch.
Thanks.
Awesome.
Okay.
Thank you so much.
Thank you, Kale. Thank you.
So Carl, I estimate that you have just short of 40 minutes for your turn. Do you think that's sufficient?
Yes, well, yeah, no, it's only 20 minutes now, but that was yeah. So before we lose that last thread, Takuya will have to go to bed now. So it will be. I think it'd be good if you could send Takuya the recording of this afternoon's or the session later today with Kyle, and then Takuya can catch up by watching the recording, and he can also get his night's sleep. I think that's probably that's why we're meeting early in the morning. Okay, so sorry, Peter, do you want me to summarize to the extent I can? Like Peter, a lot of this is very new to me. I did quantum physics when I was in my 20s, but I've forgotten it all, and certainly it's clearly moved on a lot since I was at university. So, like Peter, my comments are not going to be technically very informed. However, having said that, I mean, this sounds absolutely brilliant, and a lot of very useful joining the dots and linking different perspectives on the underlying belief updating and density dynamics that I think is the best way of describing self-organization, and in particular systems that make sense of things and make decisions in the spirit of active inference. So just to address the big question, do you sell this to a neuroscience audience, or do you, first of all, focus on engineering. I think I think you should sort of keep above both really, and um, try to pitch it as something that would be of great interest both to neuroscientists and to computer scientists, and in particular sort of quantum computation stakeholders, by going for something like sort of physics of life reviews, or the more theoretical literature, which people will read from both sides without at this stage committing to a neuronal implementation at the quantum scale. Um, and that would, I think, be best sold in the spirit, exactly as you sort of said, that one can now appeal to the calculus and the operators one finds in quantum mechanics, and these you know um, compelling algorithms such as Grover's algorithm, um, as the formal basis of something that can be implemented on a classical computer. So a lot of sort of quantum computation is actually done on a classical on a von Neumann architecture, but just borrowing um, the operators and the algorithms from the quantum information theory. And I mentioned sort of quantum information theory because if you frame this in terms of quantum information theory, you're not committing to an actual implementation at the quantum scale, below Planck's constant, for below or at the Planck scale. So I would counsel you do that first, and then having established the underlying mechanics, the quantum mechanics or the Bayesian mechanics of framed in terms of quantum computation, you can then move on to the actual substrate dependent implementation, which could be at at a Planck scale, and then you could appeal to your magneto-sensitive birds and single computation within the neuron, or indeed within the dendrite, where there is actually quantum effects can actually be physically realized and instantiated. But at this stage, I don't think you need to do that. You can just at the end of the paper say that we have formulated the mathematical and the information theoretic imperatives and the functional forms of the operators in the spirit of quantum information theory, noting that this could be implemented on a von Neumann architecture, and one can simulate quantum computation on a von Neumann architecture. But one can also think about mortal computation, substrate dependent mortal computation, actually in terms of processes at the Planck scale, intracellular processes, and then leave that story for the next phase of of the program. There's and in so doing, I think you can. Well, I've got a couple of just two papers, in fact, one paper which might be useful, um, to tell that story, which I'll show you in a minute. And I'm thinking in particular the work of Chris Fields on quantum information theory and how it leads to neuromorphic computation. What I'm trying to say here is that um, you can do the maths, and the maths can be unpacked and simulated in a substrate independent way on a classical computer. You're using probability amplitudes and complex representations and Krauss operators and the like. Or you can say, well, this maths could also be implemented neuromorphically in a substrate dependent fashion in the spirit of mortal computation, as opposed to the immortal software that you would get just by writing it down in terms of quantum information theory. So I think that will be the easiest way forward in terms of motivating this. What I like about this is the isomorphisms and the symmetry and the functional forms of the quantum formulation, and the I think that was on the previous slide where you were able to write down variational free energy purely in terms of quantum operators and Krauss operators, for example. I think this is really nice, and certainly people in neuroscience who understand um, partially observed Markov decision processes and discrete state space models and belief updating will, I think, be able to intuit what's going on here, and certainly the way that you unpacked the von Neumann entropy and the relative entropies. I think people will easily understand how that relates to Shannon entropy, classical Shannon entropies, relative entropies, and that will, I think, give people an easy access into why this works. And once you've done that, then you can say, well, okay, now we've reformulated belief updating or belief propagation or density dynamics in a quantum context. Now we can move on to the algorithms that people have discovered within quantum computation, such as Grover's algorithm. And then you can move on to your next bit. I didn't really understand, the particular implementation of the Grover's algorithm, but I can see how it's a lovely example of how one could leverage advances in quantum mechanics or quantum information theory to make it work to solve problems, particularly in terms of sort of efficient computation that are that are very prevalent in the sort of in the classical space. And then that reminds me to make the point you start in terms of domains of application.
Yeah.
You started by saying, well, there is a local minima problem, and then you went straight to the structure learning problem in the sense. Well, I understood one particular application here is not so much inference about latent states, but inference about the model itself, where you don't have any differentiability and you have to you have to actually score all the different models that could possibly explain these data. And very often that's framed in terms of a structure learning problem, and then elaborating a space of generative models and then scoring them in the right way to identify the best one. That's a very difficult problem with lots and lots of local minima. And that would potentially be one really exciting application of a quantum formulation. However, the actual examples you then demonstrated spoke to not the structure learning problem or inference on models, but actually inference on latent states under a given model. So, for example, the blind source separation, which was, I think, a nice place to start. And then you moved to state space, discrete state space models with dynamics, and that I think that's an important next step. So start off with the simplest problem, which assume you know the right model, and therefore you just need to identify or identify the latent states and parameters appropriate for that particular problem. Then move on to state space models with dynamics, which would be the predictive coding version. It might be good not to emphasize too much predictive coding. And the reason I say that is, by definition, predictive coding applies to continuous state space models, so for which you would use something like Kalman filtering. And the whole point of the quantum formulation is that you're dealing effectively with Hilbert spaces and discrete state spaces. So it may be better just to go for a discrete state space example when to emphasize. Sorry, my answer phone is going off. I'm trying to ignore it. Just to emphasize that the quantum approach does explicitly cast everything in terms of discrete states, categorical states. That you can, if you use sufficient number of them, you can then certainly sort of move towards continuous state space representations. But the mechanics of it, so, as soon as you start to deal with sufficient statistics of exponential distributions have a very different look and feel from how you'd actually write down your unitary operators, for example. Whereas if you just go for a standard POMDP like example as a sort of classical starting point or point of reference for state space models with transition probabilities or tensors, then I think you can say, well, these the equivalent unitary operators in a quantum formulation just correspond either to a likelihood mapping or to a state transition tensor, suitably factorized in terms of the complex roots. But both of the, I think that's absolutely right in terms of sort of building the story by applying it first of all to non-dynamic discrete state space models and then state space models with dynamics, and then you move on to the solving problems which are not sort of variational free energy minimizing problems, but expected free energy minimizing problems by thinking about tree searches into the future, which is another application, but still not yet, but not actually making inferences over models themselves. So it might be good just to sort of start off by saying the potential application domains here are large, and they range from simply inferring latent states under very simple discrete state space models, right through to making inferring the very structure or the nature of the generative models, discrete state space generative models that might be used to infer the states and then the parameters and then the policies, so that people know exactly what kind of problem you're tackling and where you are actually going to deploy the benefits of quantum computation and efficiency. So that people have a roadmap in mind where you're going, even within the sort of immortal computation. You're just using the mechanics to solve problems that people are contending with in classical formulations. The other point I really liked about this is that, and it might help, and perhaps I should just remind myself, if I can share, I'll just put the particular papers up that were reminding me to, or will remind me of the points that need to be made in the remaining 10 minutes. I'm sorry about this, but we do need to get you to bed at the appropriate time. Yes, right. So good. Where are we? We want the. Oh, yeah, right. Before I forget, just in relation to the conversation that you had with Peter about non-commuting operators and the sometime and then sort of non-classical inference that can ensue when your operators don't commute, and what implications that might have for explaining um, um, sort of cognitive decisions. There's the person in the UK that's been promoting this the most is a gentleman called Dorji Brody. This is quite an old paper from 1996, but he's just basically one of many people telling a story that um, the increased latitude you have when you're working with density matrices to get and non-commuting operators may explain the odd kinds of decisions that some people might make. I personally don't think that's very useful, you know, but it does speak to a certain interest in quantum inference and cubism from cognitive scientists who like to think that some people make non-Bayes optimal decisions and why, and then they look to this sort of quantum computation to give you a sort of non-classical optimal decision-making like behaviors. I don't think it's very useful, but it's something that you should be courteously acknowledging
Right.
is a field, and we can talk at another time about why I don't think it's particularly useful. But there is that community out there, so it would be useful just to mention them should you have to. This is a paper that I thought would be most interesting for you in the sense that it's promoting quantum information theory and the importance of unitary operators and the principle of unitarity in the sense with a particular agenda that's showing that in combination with or applying the free energy principle as, if you like, the principle of unitarity in the quantum information theoretic sense, it induces a neuromorphic explanation, which is exactly where you were going in terms of how this might be implemented in a substrate dependent mortal neuromorphic kind of way. The other interesting point of contact is that they sort of focus in on tensor or topological quantum neural networks, basically tensor networks, which will also interest not only you but also Philip as the natural way of or one way of understanding quantum computation. This author here, where is he? Jim Glazebrook, very much likes a particular version, a particular corner of category theory, and sort of unpacks the implicit tensor operations and the unitary operators in terms of category theory. It's a bit abstract, but it might be just a useful pointer to say that this kind of formalism may have an important role in unifying different perspectives on computation and certainly linking quantum computation, tensor networks, and category theory to inference in a classical sense. May be useful. Oh, it's got Mike Levin as well, which is he's one of the key neuromorphic people. So I thought that might be useful. You mentioned curiosity and creativity. I just put this paper up at the beginning just to reinforce this notion that certainly insight may be best understood as committing to a particular new hypothesis or model. In this particular paper, that commitment was enabled through a process of Bayesian model selection or Bayesian model reduction specifically. But the key point that I wanted to make is that hypotheses or models are discrete objects. And because they're discrete objects, you can cast insight as basically identifying a discrete object. And in being discrete, then there is now a natural role for quantum computation, which deals with probability distributions or amplitudes over discrete spaces or discrete outcomes. So that would be one nice way of just motivating the potential utility of quantum computation in terms of applying to a domain that has a discrete aspect and a really important domain, which is basically finding the discrete hypothesis or world model that best explains your lived world. Oh, just just again a historical thing for your entertainment. So, um, you mentioned the algorithmic complexity and the Turing formulations, and I'm always mindful that there was a sort of historical route to free energy minimization provided by algorithmic complexity that was picked up on by David McCabe very, very early on in the context of cryptanalysis and decoding of discrete strings. Again, this is just for historical interest, but it does speak to an interesting history that starts in this instance with the Russian literature on Kolmogorov complexity, then developed into things like Solomonov induction, that then became the basis of universal computation. Again, this story starts with discrete bits. It starts with algorithmic complexity on discrete binary, but binary bits, and that would be the sort of, if you like, the alternative route to variational free energy minimization, to Richard Feynman, who was dealing with continuous state spaces. So, just in terms of motivating quantum approaches, in virtue of they gracefully handle density dynamics on discrete state spaces, or where you move into a Hilbert space when you're dealing with the actual densities themselves. Um, you know, Sorry, I repeat, it's nice just to celebrate that there is a sort of variation free energy minimizing perspective afforded by this algorithmic complexity story. And yeah, that was basically what I wanted to say. For those, this is not for you, Takuya, but for those people who just want a simple notion of the distinction between the way that Takuya used the notion of waves, and kept re-emphasizing that it was the square of the modulus of the wave that was a probability in and of itself. Um, one way to intuit that is that it's perfectly possible to, well, the position taken by the particular physics monograph is that all processes of interest, and certainly their description, is in terms of density dynamics, probability density dynamics. There is no other description of the universe, whether it's quantum mechanics, statistical mechanics, and even the limiting case of conservative dynamics, classical mechanics. They are all derivable from the density dynamics, the how probability distributions change in time. And that means that you've got a choice. You can actually work with the sufficient statistics of a probability distribution over some states, and work out how those change with time. And that would be sort of a classical approach. Or you can work with the complex square root of the probability densities. So the sufficient statistics now become the square root of the probability densities, and then work out their dynamics in exactly the way, Takuya, that you were showing in terms of sort of row density matrix Tor relative to Tor plus one or Tor minus one. So implicit in some of your early examples was, to my mind, a very compelling description of density dynamics. But here the densities were written down in terms of square roots or complex roots. That just is the quantum formulation. And one helpful trick I found in writing this paper is to answer the question, why would you want to work with square roots? Why don't you just work with the probability densities as opposed to the square roots, the probability amplitudes, for example? Well, the beauty of working with the square roots is you can now do Fourier transforms. And you can appeal to Wiener-Klintine theorems and all the theorems that lead to Heisenberg uncertainty principles and the like. And of course, once you can work in the Fourier transform space, because you're working with the square roots, you can now talk about waves and solutions and wave equations and the like. But the point I'm making here is that just to stop people being frightened who don't know about quantum mechanics, you can tell them all that you are doing is now just writing down density dynamics in terms of the complex roots of a probability density. So it's taking the Bohm rule? Yeah, it's saying you don't need any axioms anymore. You just say that it's all about density dynamics. You've got you can pick different ways of describing the probability densities, if you commit to working with probability amplitudes, there are certain advantages. We are going to pursue this. This is known as quantum mechanics. And in particular, if we now apply it to discrete state spaces, we can now do all this quantum mechanics just with linear operators. And this vastly simplifies the all the sort of the derivations and the maths, and speaks to a potential efficiency and flexibility which you wouldn't get if you didn't make these quantum commitments. So that was just advice in terms of making sure that people are not frightened by having to learn about quantum mechanics, sometimes again, and saying why they should be interested. What are the potential benefits of just now rewriting density dynamics, as say a variation-free energy minimizing process in a quantum formulation. So you can just list why they might be interested. And once you've done that, then you can show them how easy it is to get from a classical POMDP formulation with A and B matrices to these unitary operators or the Krauss operators, dealing with the square roots of everything. Sort of, A conjugate transpose times A just is your likelihood mapping. B conjugate transpose, just explaining, you're just working with the square roots. And this has enormous advantages because I can now express everything in terms of simple linear algebra. And don't be frightened by the Dirac notation. It's just one way of very compactly writing down linear algebra. Furthermore, we can now speak to things like the Schrodinger wave equation because we can also do Fourier transforms, on the probability amplitudes, which is not so easy to do if you're actually working with the probability densities in and of themselves. And with that, I'm going to have to leave you and hope that you can. Thank you for a brilliant presentation.
Thank you very much.
And I look forward to hearing what happens next.
Yes. Thank you. Thank you very much. A lot of feedback.
Let's do a final round of applause for Takuya before he goes to bed.
Thank you.
Thank you everyone
Bye.
for coming.
Thank
you
you
for the
very much.
presentation, Takuya. Till next time.
Yes. Thank you. Thank you. Bye.